My name is Sayantan, and if that name is too difficult for you to remember, you can just call me Sai. And I guess Sai is the easiest name to remember at a quantum conference. So today I'll be talking about the cost of training quantum models. I will introduce new algorithms that can be used to reduce that cost, that said cost. And towards the end, I'll spend a couple of minutes also talking about the cost of training robust quantum models. Before we start with the algorithms, I'm sorry, the clicker is not. Thank you. Before we start with the algorithms, let me motivate the problem a bit. Let's suppose that you wanted to train a quantum model to classify 2 digits of the MNIST data set. You have a model with about 120 parameters. You only have 100 training examples across both classes combined. And you want to run 100 iterations of stochastic gradient descent. And maybe you want to train this on a real quantum processor, which is superconducting and is available through a provider like AWS. Then the cost that you would incur to train this model is of the order of $1.5 million US. To put this into perspective, you can train a similar analogous classical model in a matter of minutes or seconds on the laptops you're holding right now. So a major part of this cost comes from the large number of circuits that has to be executed to train these models. And circuit execution is something that we will try to reduce in today's talk. I know that I don't have to introduce variational quantum algorithms to this audience, so I'll jump directly to the problem of empirical risk minimization. The equation that you see on the screen is the empirical risk, and we want to minimize this over parameters which are d-dimensional real vectors. And the objective is to reach an epsilon-stationary solution in the expected sense. What is quantum about all of this? The hypothesis function of the model is. And it's all pretty standard. We have been familiar with this for many years now. The circuit looks like this. We start with the conventional 0 state, and then we encode the data using angle embedding. And then we apply a couple of layers of a variational ansatz, and we end with measuring a Hermitian observable H. So the assumptions that we will adhere to for the remainder of this talk are that the circuit only consists of X, Y, and Z rotation gates and C0 gates. And the parameters that go into these rotation gates, they are uncorrelated with each other. So out of the d-dimensional vector, if you pick a theta I and a theta j, they are going to be uncorrelated. And the third and final assumption is that we don't have access to the exact objective function values. We only have access to stochastic estimates, which are unbiased. And the estimator variance is also bounded by a quantity, sigma squared. Before we move on to the algorithms again, we should spend a couple of minutes talking about the smoothness of the loss function. And the smoothness is important because it has important implications in finding the convergence rates of these algorithms. It also helps us find the feasible step sizes that we can use with these algorithms and so on. So when I say smoothness, I just mean the standard definition of Lipschitz smoothness that you can see on the screen. And it can be shown that the expectation values that we calculate for the kind of circuit that I have shown, the smoothness is of the order of d, where d again is the number of parameters we have in the circuit. And under very fairly generic assumptions, we can show that the empirical risk is also order of d smooth. And one final thing before we move on to the algorithms is, we are all familiar with the parameter shift rules, which can be used to compute the gradients and the derivatives with respect to the parameters in a quantum circuit. But one problem with the parameter shift rules is, if we want to calculate the entire gradient vector, if we want to estimate it, then we need to run 2D number of circuit executions to do that. And although this might seem very innocent and innocuous because it's only linear in the number of parameters, this has pretty big implications in the number of circuit executions we need with gradient-based algorithms. Next, there is stochastic gradient descent. I'll not talk about the steps of stochastic gradient descent, but I would like to point out that SGD needs of the order of L d square over epsilon to the power 4 circuit executions to reach an epsilon-stationary solution. And this is huge because it's cubic in the number of parameters. So if you increase the number of parameters, your number of circuit executions you need increases cubically. And if someone thinks that they can sidestep this huge cost by only updating one of the parameters at each iteration by picking them randomly, that kind of a scheme is called random coordinate descent. And it can be shown that random coordinate descent also has a similar convergence rate as stochastic gradient descent. So that is not going to help. Now I'll introduce the new algorithm, which is called stochastic 3 points method. And what this algorithm does is, it's a zeroth order method, it's gradient free. So at each iteration, it samples a random vector from a standard normal distribution. Then what it does is, it calculates 2 different points. If theta t is the current iterate we have at the tth iteration, then it calculates theta plus, which is theta plus alpha times v. V is the random vector, and a is a positive step size, and theta minus similarly, which is theta minus alpha v. And we evaluate the objective function at these 2 points. We already have the objective function from at theta from the previous iteration. And the way we update the parameters is, whichever of these 3 points gives us the lowest objective value, we take that as the next iterate. It's just as simple as that. And for this very simple algorithm, we can show that the rate of convergence is of the order of LD over epsilon squared. So it's an improvement over what we get with stochastic gradient descent. And the important thing to note here is, we only need 2 circuit executions per iteration with this algorithm. Instead of 2 D circuit executions, we would need with a full gradient-based algorithm. But there are some problems and caveats with this STP method. The first problem is that I haven't talked about what kind of step sizes we can use with this method. And the step size, the feasible step sizes are given by this expression. And at this point, you might feel a little cheated because the feasible step size itself depends on the directional derivative, the modulus of the directional derivative at the tth iteration. And the directional derivative itself depends on the gradient. So it kind of seems to defeat the entire purpose of gradient-free optimizer, where we don't want to compute the gradients at all. There are a couple of ways to handle this. My favorite way is that there hasn't been a lot of research in how unbiased estimators of directional derivatives can be computed. But I'm happy to report that we can show that this actually can be done very efficiently with only execution of 2 circuits. But the fine print here is that the circuits that we are talking about, they come with an increased number of qubits and with an increased depth. And this paper appeared on arXiv this morning, only a couple of hours ago. I have a lot of backup slides on this, so if you have any questions, then please do ask. The next problem that we have with, the other ways that we can deal with these issues are the mundane ways. We can just perform a grid search over the step sizes, over a range of step sizes, and select the best one. Or we can use some kind of probabilistic arguments. Like this is an event that L times alpha should be less than the absolute value of the directional derivative. And we can bound this probability so that it's always equal to 1. And if we do that, we'll see that the step size alpha, which is feasible, depends on this expression on the screen. This again depends on the norm of the gradient, but this also can be handled for specific kinds of functions which are gradient dominated. So for example, convex functions are gradient dominated. Functions that obey the PL inequality, they are gradient dominated. Or if we have a observable which is positive semi-definite, then the gradient norm can be lower bounded by the minimum eigenvalue of the PSD observable. The other problem that we have with STP is the previous algorithm I showed assumes that we have access to the exact objective values, which we don't. We have already discussed that we only have access to unbiased estimators of the objective values. So the minimum argument that we pick over the unbiased estimators might not be the same as the minimum argument we pick over the exact objective values. and these arguments might differ with, say, a probability delta. So in the stochastic case, the new update rule is just pick the one which gives the minimum stochastic estimate of the objective value. And in that case also, it can be shown that the order of convergence of STP does not change much. It is still of the order of LD over epsilon squared. But in the denominator, we have an extra factor of 1 minus 2 delta squared, where delta is the failure probability. So it's easy to see that if delta is half, that is, we fail with a probability of half, that means STP will basically need an infinite number of iterations to converge. We will not get anywhere. So in summary, what we have done so far is, with SGD, the order of convergence or the number of circuit executions was LD square over epsilon to the 4, and we have reduced that to LD over epsilon squared. Now, if in the audience, if there are experts on zeroth order optimization, they will raise an objection because I seem to be doing better than the optimal rates that are possible with gradient-free methods. But I'm actually not claiming that because there are other nuances with the STP method that I don't have time to discuss now. But if you're interested, if you're curious, then please talk to me after the presentation. So as we have discussed a couple of times now, we only have access to unbiased estimators. But how many shots should we use to calculate those unbiased estimators? If we want to ensure that we are epsilon close to the argmin or the minimum of the objective function over these 3 points, and we want to have that with a probability of at least 1 minus delta, then this is the number of shots we should use for each evaluation of the objective function or the expectation values. So to show some results that we get with STP, this is again a very standard experiment we perform for quantum machine learning. We try to classify between the digits 3 and 5, and we use a quantum circuit which has 120 parameters. These are the training plots for different algorithms like SGD, SPSA, random coordinate descent, and 2 variants of STP. One of the variants of STP has a fixed step size, and the other variant has diminishing step sizes. We see that with random coordinate descent and SPSA, we don't really get much of a reduction in the training loss. It stays fairly constant. And the 2 STP versions, they perform better, but they are still not close to the performance we get with SGD. But this plot does not show the exact picture. This other plot shows the exact same data, but now on the x-axis, we have the number of circuits that are executed, and this x-axis is on a log scale. And here we'll find that the number of circuit executions that STP requires is about 100 times lower than the circuit executions that SGD requires. And because of the effect of delta, which is the failure probability, we see that STP also shows an early convergence, and it cannot reach the same objective value as SGD can. And in the final couple of minutes, I'll just talk a little about robust training of these quantum models. And robust training is sometimes done with this kind of an adversarial loss. This is a famous example of a loss where the loss function is regularized with the squared norm of the gradient of the loss function, but the gradient is taken with respect to the input features, not with respect to the parameters. So in this case, what happens is computing the gradient with respect to theta was hard enough. Now if we need to compute the gradients with respect to the features, that just adds extra cost to our training algorithm. But if we consider angle encoding for embedding the features, and for the sake of simplicity, if we say that the loss function is linear in terms of the expectation value, and that the eigenvalues of the Hamiltonian, they are positive and lie in the range of 0 to 1, then the squared gradient of the norm, squared norm of the gradient with respect to x can be upper bounded by this quantity 4n times the actual loss, where n is the dimensionality of the input features. So the implication of this is that the adversarial loss that we saw on the previous screen is upper bounded and lower bounded by scalar multiples of the loss function. So maybe we don't need to use the adversarial loss at all. We can just train the model with the natural empirical loss that we train it with. I was initially excited about this result, and this experiment kind of confirmed our hypothesis because we performed adversarial training with a bunch of adversarial defense parameters, and we also performed non-adversarial regular training, and the performance of the regular classifier is almost on par with that of the adversarially trained classifiers. But later it got me thinking that if we take a function, if we consider an arbitrary function which is smooth and which only takes positive values, or rather non-negative values, then for the arbitrary function g, we can still write this expression where the squared gradient norm is upper bounded by L bar times g of phi, where L bar is the smoothness constant of the function g, Lipschitz smoothness constant. And this is something we can write for any arbitrary function. So this should mean that an arbitrary smooth non-negative function should not benefit from adversarial training. But that is not the case we see with classical machine learning, because adversarial training obviously does help. So this result kind of now confuses me. If there is anyone in the audience who can shed more light on it or would like to investigate it further, then please do get in touch with me. That is all I had for the purpose of this presentation. Thank you for your attention.